Picture this, you're standing in the Smithsonian's Paleontology Hall. Behind glass, stretched across an entire wall, lies the reconstruction of a snake so massive it defies belief. 42 feet long, a body thicker than a man's torso, a skull the size of a microwave oven. For 15 years, that display has represented a scientific consensus. Titanoboa sarajonensis, the largest snake ever discovered. But walk into paleontology conferences today, scan the latest journals, and you'll notice something has shifted. Scientists are no longer speaking in absolutes. The language has become cautious. Titanoboa is now described as the largest known snake, but recently contested. That shift from certainty to debate marks one of the most dramatic reversals in modern paleontology. Because in the depths of an Indian coal mine, scientists unearthed something that shouldn't exist: 27 vertebrae belonging to a snake that may have matched or even exceeded Titanoboa's size. Its name is Vasuki indicus, and it has reignited a debate the scientific community thought was settled. Here's what makes this story extraordinary. Titanoboa wasn't just a record holder, it was a thermometer. Scientists used its size to calculate ancient temperatures, to model prehistoric climates, to understand what Earth looked like 60 million years ago. Museums rewrote their exhibits. Documentaries framed it as the apex predator of a lost world. Textbooks called it the ultimate snake. But Vasuki changes the equation. Because if Vasuki was equally large or larger, then either our methods for estimating size are flawed, or giant snakes weren't confined to the steaming jungles of Paleocene Colombia. They lived across continents. They thrived in different climates. And that means everything we thought we understood about the limits of snake size may need to be reconsidered. This isn't a story about one snake replacing another. It's a story about the fragility of scientific certainty, about how a handful of bones can rewrite history, about what happens when two fossils, separated by 13 million years and 5,000 miles, force us to ask a question we thought we'd already answered. What is the largest snake that ever lived? And right now, the answer is, we're not entirely sure anymore. The story begins in February 2009, when a team led by paleontologist Jason Head published findings in Nature that stunned the scientific world. They had discovered the fossilized remains of a colossal snake in the Sarajon Formation of northern Colombia, a 60-million-year-old coal mine that once was a tropical rainforest. The fossils included vertebrae up to 5 inches wide, nearly twice the size of the largest modern anaconda vertebrae. By comparing the proportions to living boas and anacondas, the team estimated the snake's total length at approximately 12.8 meters, roughly 42 feet, with a possible range of 37 to 47 feet. Weight estimates placed it at 730 to 1,135 kilograms. That's 1,600 to 2,500 pounds. For context, the largest green anacondas alive today max out around 550 pounds and 30 feet. Titanoboa wasn't just big. It was twice the mass and half again the length of any snake alive today. But here's what made Titanoboa more than a curiosity. It became a climate proxy. Snakes are ectotherms, cold-blooded animals whose size is constrained by environmental temperature. The larger the snake, the warmer the habitat must be to support its metabolic needs. Head and his colleagues used Titanoboa's size to back-calculate the mean annual temperature of Paleocene Colombia. Their conclusion: the environment averaged 30 to 34 degrees Celsius, that's 86 to 93 degrees Fahrenheit, significantly hotter than modern tropical rainforests, which average around 77 to 82 degrees F. This was a revelation. It validated climate models predicting a greenhouse Earth in the Paleocene, a time when atmospheric CO2 levels were far higher than today and polar ice caps didn't exist. Suddenly, Titanoboa wasn't just a snake. It was a living thermometer frozen in stone. Museums embraced the discovery. The Smithsonian built a life-size model. Documentaries depicted Titanoboa gliding through steaming swamps, ambushing prehistoric crocodiles. It became the poster child for a lost, hotter world. For 15 years, the science seemed settled. Titanoboa was the largest, the methods were sound, the climate implications were clear. And then in April 2024, everything changed. In the Nerdi Formation of Gujarat, India, paleontologists Debajit Datta and Sunil Bajpai uncovered 27 vertebrae belonging to an enormous snake. The fossils dated to the Middle Eocene, approximately 47 million years ago. That's 13 million years after Titanoboa, in a completely different part of the world. The snake was named Vasuki indicus, after the serpent deity of Hindu mythology that coils around the god Shiva's neck. And here's where the debate begins. The vertebrae suggested a snake of extraordinary size, using multiple estimation methods because Vasuki belongs to an extinct family called Madsvidae with no living relatives for direct comparison. The researchers calculated a length range of 10.9 to 15.2 meters. That's roughly 36 to 50 feet. The upper end of that range would make Vasuki longer than Titanoboa's mean estimate, but the uncertainty is substantial. The lower end puts it smaller than Titanoboa. The ranges overlap. So which is larger? The honest answer is we can't be certain. Here's why. Titanoboa's size estimate was based on scaling relationships derived from modern boas and anacondas, snakes with living relatives whose body proportions are well understood. The assumption, vertebral width correlates predictably with total body length. But Vasuki poses a problem. Madsvids are extinct, they have no living descendants, their body proportions may have been different. Data and Bajpai used multiple methods, comparing Vasuki to both modern snakes and other extinct giants, but each method yields a different estimate. Some analyses suggest Vasuki could have reached 15 meters. Others place it closer to 11 meters, still massive but smaller than Titanoboa. And here's an important consideration. Researchers have noted that extrapolating from modern snakes to extreme fossil sizes carries inherent uncertainty. Nonlinear growth patterns in truly giant snakes can complicate scaling models. If such patterns existed in Titanoboa, its original size estimate might fall closer to 11 or 12 meters, not 12.8. Suddenly, the question isn't which is larger. It's how do we even measure size accurately when dealing with incomplete fossils and extinct body plans? To understand why this debate matters, we need to grasp a fundamental challenge in paleontology. You almost never find a complete skeleton. Titanoboa is known from multiple vertebrae and ribs, but no complete spine. Vasuki is known from 27 vertebrae, again incomplete. To estimate total length, scientists use scaling laws, mathematical relationships between vertebral dimensions and body length in living snakes. For Titanoboa, the team measured the width of the largest vertebrae and compared them to those of modern boas and anacondas. In living snakes, vertebral width scales predictably with body length. Apply that ratio to Titanoboa's massive vertebrae and you get an estimate of 42 feet. But here's the problem, scaling isn't always linear in the largest individuals. In modern anacondas, the largest specimens show proportionally wider vertebrae than smaller individuals. This suggests that as snakes grow to extreme sizes, their vertebrae thicken disproportionately, perhaps to support the increased weight. If Titanoboa followed a similar pattern, using a linear scaling law might produce a range of uncertainty. This is a known challenge in paleontology. When you push biological models to their extremes, the biggest, the smallest, the most unusual prediction errors grow. The further you extrapolate from known data, the wider the confidence intervals become. Vasuki complicates this further. Madsvids weren't closely related to boas. Their vertebrae had different shapes, different articulation surfaces, different proportions. Data and Bajpai addressed this by using multiple methods, comparing Vasuki to boids to other madsvids to generalize snake models. The results varied by method, hence the wide range of 36 to 50 feet. And here's where it gets scientifically thorny. If the scaling methods are uncertain, so are the climate inferences. Remember, Titanoboa's size was used to estimate Paleocene temperatures. The logic: a snake this large requires a hot environment. Calculate the minimum temperature needed to support such a body mass and you get 86 to 93 degrees F. But if Titanoboa was slightly smaller, say 38 feet instead of 42, the temperature estimate drops. Maybe Paleocene Columbia was closer to 82 to 88 degrees F, still warm but not as extreme. And if Vasuki was equally large in the cooler Eocene, it suggests that giant snakes could tolerate a wider range of temperatures than previously thought. That challenges the entire snake thermometer model. Some paleoclimatologists caution against overinterpreting single fossils. They point to other temperature proxies, leaf fossils, isotope ratios in marine shells, ancient soil chemistry that provide independent lines of evidence. When multiple proxies agree, confidence grows. When one outlier appears, it's a signal to re-examine assumptions. The debate isn't just about which snake was bigger. It's about how we use fossils to infer ancient environments, and whether our methods are robust enough to handle edge cases like these. Step back from the measurement debate for a moment, and a bigger picture emerges, one that tells us something profound about the limits of life on Earth. Giant snakes like Titanoboa and Vasuki represent the upper boundary of what's physiologically possible for a limbless, elongated predator. Understanding why they got so large and why modern snakes don't reveals the interplay of climate, ecology, and evolution. First, climate and metabolism. Snakes are ectotherms. Their body temperature matches their environment. In cold climates, metabolism slows. In hot climates, it accelerates. Larger body mass offers an advantage in warm environments, thermal inertia. A big snake heats up slowly and cools down slowly, maintaining a more stable core temperature than a small snake. But there's a trade-off. Larger snakes require more food. A 2,000-pound Titanoboa would have needed large, regular meals, likely on the order of tens to hundreds of pounds over weeks or months, depending on metabolic rate and feeding intervals. In a hot, productive tropical ecosystem like Paleocene Colombia, teeming with giant turtles, crocodilians, and fish, Titanoboa could meet those needs. The environment was an all-you-can-eat buffet. But maintaining that size in a cooler or less productive environment, much harder. Second, prey availability. Both Titanoboa and Vasuki lived in ecosystems dominated by large aquatic and semi-aquatic vertebrates. Titanoboa shared its swamp with 5-foot-long lungfish and crocodile-like dinosaurids. Vasuki coexisted with prehistoric crocodiles and large fish in Eocene India. These snakes likely employed ambush tactics, lying motionless in murky water, then striking with bone-crushing force. Modern anacondas use constriction to subdue prey as large as caimans. Titanoboa and Vasuki likely did the same, but at a scale that dwarfs anything alive today. Third, competition and ecological niches. Why don't we have snakes this large today? The simple answer: the world is cooler and the giants are gone. Modern tropical ecosystems are productive, but they don't match the greenhouse conditions of the Paleocene. Average temperatures are 5 to 10 degrees Fahrenheit lower. That reduces metabolic rates, limits prey size, and makes it harder for a giant snake to find enough food. Moreover, modern ecosystems are shaped by competition from other apex predators, jaguars, crocodiles, large raptors, that didn't exist in the same form 60 million years ago. Titanoboa faced less competition. It was the apex aquatic predator in its environment. Fourth, evolutionary constraints. Snake body plans impose physical limits. As snakes grow longer, their body must support increasing weight, vertebrae must thicken, muscles must strengthen, internal organs, heart, lungs, digestive tract must scale appropriately. There's likely a biomechanical ceiling beyond which a snake's body plan becomes unsustainable. We may be witnessing that ceiling in Titanoboa and Vasuki, snakes pushing the absolute limits of what their anatomy allows. The fact that both lived in aquatic or semi-aquatic environments is telling. Water provides buoyancy, reducing the mechanical stress of supporting a massive body. It's no accident that the largest snakes, both ancient and modern, are strongly associated with rivers and swamps. So here's where we stand. Titanoboa, discovered in the coal mines of Colombia, remains the most completely understood giant snake in the fossil record. Its estimated length of 42 feet is based on well-studied scaling relationships with modern boas and anacondas. Its role as a climate proxy has shaped our understanding of Paleocene greenhouse conditions. Museums around the world still feature Titanoboa as the largest snake known. But Vasuki has introduced uncertainty. With a size range of 36 to 50 feet, it may have equaled or exceeded Titanoboa, but the margins of error are large. The lack of living relatives makes precise scaling difficult. And its existence in the Middle Eocene of India, a different time, a different place, suggests that giant snakes weren't unique to a single hot moment in Earth's history. Some scientists now argue that we need better methods for estimating size from incomplete fossils. Others suggest that the largest snake question is less important than understanding the ecological and climatic conditions that allowed such giants to exist. Here's what we can say with confidence. First, both Titanoboa and Vasuki represent the upper limits of snake size, likely constrained by biomechanics, climate, and prey availability. Second, gigantism in snakes occurred multiple times across deep time in different environments. It wasn't a one-off evolutionary experiment. Third, our methods for estimating size from fossils carry significant uncertainty, especially when dealing with extinct lineages and incomplete skeletons. As new fossils are discovered, and as techniques like CT scanning and computational modeling improve, we may eventually settle the question. For now, the safest answer is this: Titanoboa remains the default reference, the best-studied giant, the snake that changed how we think about prehistoric climates. But Vasuki has reopened the door. And in science, an open door is often more valuable than a closed case. Because the moment we stop asking questions, the moment we assume the debate is settled, is the moment we stop learning. Titanoboa taught us that the past was hotter than we imagined. Vasuki is teaching us that our imagination still has room to grow. The largest snake debate, it's not over, it's just getting started.